Alrighty, now that we're done dealing with parametric review, why don't we go ahead and just jump right in with some calculus of parametrics. This is 10.2 in the Stewart book. So let's go ahead and let's jump in with taking the first derivative. Now, if I'm asked for dy dx, but I have x and y independently in terms of t, it should make sense. And y is equal to 3t minus 1 or something like that. And I want to get dy dx. What I need to do is I just need to say, well, dy dx is equal to dy dt, which is 3, over dx dt, which is 1/2 x to the negative 1/2. Okay? Which winds up being, this winds up being 3 over 1 2 root x, or 6 root x. Okay? Actually, root t, sorry. Root t. So, my bad. Okay. Now, I have dy dx in terms of t. So if I wanted to actually evaluate it at a specific point, like, what is dy dx when t is equal to, I don't know, let's say 1, then it would just be 6 root 1 or 6, right? So you can actually evaluate the first derivative at a particular point, a certain value of t, okay? So here's the weird thing, though. It's dy dx, but it's in terms of t, okay? Now, that's going to, so that was really straightforward in terms of the first derivative, but because when I'm taking the second derivative, okay, what you're really doing is you're differentiating with respect to x what you already have as dy dx. Okay, well, here's the problem with that. Dy dx is in terms of t. So unless you want to go to the Herculean effort of actually changing it all in terms of x, we need to figure out what the equivalent move is in terms of differentiating with respect to t. Well, I'm going to take this ratio right here, and I'm going to sort of unsimplify it. Okay? And so what happens here is you need to take the derivative of your original dy dx with respect to t, and then you need to divide it by a further dx dt. Okay? So here's the thing. In this particular one, you know that taking the derivative with respect to t, so if you're taking the second derivative of what we already have here, you know that you're taking ddt of 6 root t, because that is the dy dx, over the dx dt. Well, dx dt we've already figured out is 1/2 t to the negative 1/2. Okay? Well, this is the same derivative, just multiplied by 6. So what you have here is 6 times 1/2 t to the negative 1/2 over 1/2 t to the negative 1/2. That right there cancels, and what you just get here is 6. Okay? Now, does that make sense? Well, if you actually think back to the original, it makes perfect sense, because if you were actually to deal with this in terms of eliminating the parameter, this would have been x squared is equal to t, which would have made this y is equal to 3x squared minus 1, the second derivative of which is 6. Okay? So we see that it actually works out the same way. But it actually is incredibly important that you remember that taking the second derivative is not as straightforward as you would think. It's not just taking the derivative again of dx dt, because your dx dt is in terms of t with an implied relationship to x, right? So if you're taking the derivative with respect to x of an expression that is in t, you have an implied relationship between t and x that needs to be dealt with, and hence why we deal with it this way. Okay. Let's go ahead and do another example of that, just so we sort of solidify what's going on here. Okay. Oh, let's do some trig. What do you say? So we have x is equal to cosine theta, and y is equal to 3 sine theta. Now I know that that is an ellipse, okay? And I want to find the first derivative and the second derivative, and then we'll evaluate both of them at theta is equal to 0. How about that? Okay? So I know that dy dx is going to be 3 cosine theta over negative sine theta, or negative 3 cotangent theta. And if I evaluated that at 0, at theta is equal to 0, dy dx at theta is equal to 0, then I'm going to get negative 3 cotangent 0, and of course that is undefined. So apparently the slope at theta is equal to 0 is undefined, meaning that you have probably a vertical tangent line, which makes sense, right? If that's an ellipse, and of course, an ellipse is, either like this or like this, then at theta is equal to 0, to have a vertical tangent line would make a whole lot of sense. Let's go ahead and take the second derivative. Okay. Now I know that the second derivative, like I've already said, is d dt of dy dx over dx dt. Okay? So I need d dt of negative 3 cotangent theta. All of that over, I need dx dt, which we know is negative sine theta. Well, what is the derivative of cotangent theta? Well, the derivative of cotangent theta is actually pretty straightforward. You know that the negative 3 is going to come along for the ride, and you know that it's going to be negative cosecant squared theta. And then, of course, the negative sine theta continues to come along for the ride. Let's go ahead and cross those two out. And to divide by sine is to multiply by cosecant, so it's negative 3 cosecant cubed theta. Now, can I evaluate that at theta is equal to 0? And the answer is yes, okay? Now, but I automatically recognize the fact that cotangent has an implied denominator of sine, cosecant has an implied denominator of sine, so we're going to get an undefined second derivative as well. Well, that makes sense because we're dealing with a point on the right-hand side, most likely, of this, we're dealing with a point on the right-hand side of an ellipse. Does it really make sense to describe the concavity of that point right there that's along the positive x-axis, or what we would call the polar axis, theta is equal to 0? No, it really doesn't make much sense at all, so our second derivative is going to be undefined as well, okay? Let's do a third. I tell you what, let's actually move on, and let's actually use this information to determine tangent lines, okay? So let's say that we have x is equal to t squared minus 4, and y is equal to t squared minus 2t. And let's actually try and find the tangent line at, let's say, 0, 0, and negative 3, negative 1. Okay? Well, in order to find the tangent line at those particular points, I first need to go ahead and I need to find the derivative. So I know that dy dx is going to be dy dt over dx dt. dy dt is going to be 2t minus t, and dx is going to be 2t, so it's going to be t minus 1 over t. Okay? Now, you can rewrite this if you want, like that. It might be easier to take the derivative if it's like that, if you were asked to take the second derivative. I'm actually not asked to take the second derivative on this particular one. So If I'm looking for the tangent line at 0, 0, I recognize that when I actually plug in for 0, 0, I cannot plug in 0, 0 here. I'm going to need to find a t value that corresponds to 0, 0. Okay, well, when is it going to be 0, 0? Well, I mean, you can go ahead and solve for them if you want. You can go ahead and say, well, it's going to be 0 is equal to t squared minus 4. It's easy enough to solve that quadratic. 0 is equal to t squared minus 2t, and it's easy enough to solve for that one. That's going to be t plus 2 and t minus 2, and that's going to be GCF factoring. And so what they have in common is the fact that t is equal to 2 is going to give you the order pair 0, 0. Okay, which if you just sort of looked at it, you could have actually figured that out. So I'm really looking for the tangent line at t is equal to 0. So what I need to do is I need to evaluate my dy dx at t is equal to 2, and I'm going to get 2 minus 1 over 2, or 1/2. So I have my slope, I have my point. I can go point slope, except it's through the origin, so we know that it's y is equal to 1/2 x, okay? I would do exactly the same thing with -3, -1. I would set -3 equal to t squared minus 4. I would set -1 equal to t squared minus 2t, and I would find the t value that actually gives me those values. Now it's going to be t is equal to 1, okay? And so if I evaluate dy dx at t is equal to 1, I'm going to get 1 minus 1 over 1, or 0. Okay, so if my slope is going to be 0 and it goes through -3, -1, then I know that it's going to be y is equal to -1, right? Because it's a horizontal line. So I just need the y coordinate. I don't need the x coordinate. Okay? Does that make sense? I hope so. Let's go ahead and move on to something that's a little more difficult. Let's say that we're not given a particular ordered pair in order to find the tangent line. Let's say that we are given x is equal to 2 sine 2t and y is equal to 3 sine t. Okay? Now, it says find the equations of the tangent lines at the point where the curve crosses itself. Well, I tell you what, let's go ahead and remind ourselves how to do this. Now let's go to mode. Okay, I'm going to go down to parametric. Okay, and then I need to go to the y equals. I need to make sure that I'm in radians. Okay, I have one of the newfangled TI-84 plus C, so I can see the fact that I am actually in radians no matter what screen I'm on. And I know the fact that it's going to be 2 sine 2t and then 3 sine t. And let's go ahead and graph that. Actually, let's go ahead and let's go to the window and let's say -4. Let's go 0.001. -4 to 4. Delete. -4 to 4. Okay. Okay, that's actually probably a little too slow in terms of the window. Let's go 0.05, and then let's graph it. Okay, now we see that that's the shape, okay, and we know that if we go back to the window, we know that the t range was between 0 and 2 pi, okay? So we got a pretty good idea of exactly what's going to go on there. When are we going to have it where it crosses itself? Well, we can sort of reason it out in a couple of different ways. In this particular case, you know that xy is going to be, well, what's probably the best way to do this? Let's go ahead and say, oh gosh, we're getting low on time. Okay, I tell you what, let's go ahead and postpone this particular problem to the beginning of the next video, And then from there, we'll get on into talking about areas under the curve with respect to parametric equations, and how doing it with respect to parametric equations is a little bit different than doing it with regular Cartesian rectangular. Okay? Alrighty.